Hello and a warm welcome to everybody. This is a review of the in-class worksheets that we conducted during week 2 of STAT100. The first worksheet we're going to talk about is the one that covered section 2.4 to 2.7. And for question 1, part A, I asked you to draw 2 histograms from 11 data points. The first histogram was having 7 different bins, and the second histogram had 3 different bins. To help you get started, I drew up 2 different tables so that you could actually tally the number of values for each of the bins in the 2 different tables. An easy way to get your totals would then be to go through one number at a time and just put a mark where it fit on each of the tables for the 2 different histograms. So for example, you could start with number 24 here, and you realize that it would sit in the bottom bin for histogram 1, and of course the bottom bin for histogram 2 as well. The next number, number 20, goes up here, and on the other side, histogram 2, it sits in the second of the 3 bins. Likewise, for 18, we can see it is up here, and histogram 2, it is over here. Now, before we go on, I did want to note that in this particular setup, you can see that I've got the less than or equals to in the second part of the bin. So the value of 20, for example, went in the bin that I listed it there. But if these symbols were rearranged in different order, like this, that 20 would actually go in the bin below like that. So I just wanted to flag that because there was something written about it in the textbook as well. So make sure that you can see which side is the equals to sign in terms of the bin, so you know exactly which side, exactly which bin, sorry, the individual data value would fall into. So as you continue to go through that process, you're obviously going to be able to put each of your data values into a different bin for the 2 different histograms. And then obviously you sum up each of those rows so you have a total count for each of the bins. And now you are ready to draw your histograms. So here we are set up to draw our histograms. You can see I've now got the 2 axes and the graph paper showing on the left, and I've put my tables up on the right for reference so I can use them to actually draw the histograms. You'll see that I've already put the X scale on between the minimum and maximum data values that was recorded. And if you look on the at the counts, you can see that the maximum number of counts occurred in the second bin for histogram 2, and that's 5. So I can now also add an appropriate Y scale as well. Let's get started on histogram 1, so obviously the top table, and also we'll work on the graph on the left. The number of data values falling between 10 and 12 was just 1, so we can put that on our scale there, on our graph there. Between 12 and 14, there were 2 values, 1 value between 14 and 16, 2 between 16 and 18, 3 values between 18 and 20, no values between 20 and 22, so we leave that, we've got a 0 bar there. And the last category, there were 2 different values there. For the second graph, obviously we've just got 3 bins of 4, 5, and 2. So that's what it looks like there. When you compare them side by side, obviously it's easy to see that the higher number of bins you have, the more detail that you can pick up from looking at the from looking at your data set. Okay, so we can see a bit of more fine scale up and down patterns in the counts on histogram 1 as opposed to histogram 2, which obviously collates the information over a broader scale. In part B of question 1, I got you to calculate the mean as well as the 5-number summary, which is the min, Q1, median, Q3, and the max. I'm confident you guys know how to do that and can check that. But for part C, what you would do is put that 5-number summary into action via a box plot. So obviously at the end of the 2 dotted lines is the minimum and the maximum respectively. The big box in the middle, the 2 ends refer to the Q1 and the Q3, and the line in the middle of the box refers to the median. In this case, we can see that the median is actually much closer to the Q3 than the Q1. So we've got a somewhat non-symmetrical distribution in this case. All right, let's now talk about the second worksheet that we worked on during the week, and that was the one for section 3.1 to 3.2. And this is where I got you to push coins on your paper to come up with some data points to then fit a regression line. So this is what your page may have looked like. You've got 3 different distances that your coin went for the 3 different lengths of pushing that you did, and you then could fit a line of best fit here. Okay, I then asked you to try and come up with a regression equation for that. So the 2 quantities you would have needed to estimate in this case would be an intercept, which could be done by extending your line of best fit until it cut through the y-axis. And the second one was the slope. So in order to estimate the slope, you could pick any 2 points on your line, and then you would just look at the change in y between those 2 particular points divided by the change in x. We can then write these out by the correct symbols. So the y-intercept, also known as beta 0, in this case you can see it actually cuts at about 0. Slope, also known as beta 1, is approximately about 1.1 divided by 1. So we get about a 1.1 there. We can then plug this into our regression equation. Okay, so our predicted value for y, or our average y, which we also refer to as y hat, in this case would be 0, our beta 0, plus 1.1, our estimate for beta 1, and then x, because that's just our explanatory variable. Now you do realize, of course, that once you've got this general regression equation, you can then plug in values for x that you haven't taken measurements on, but are within the range of values that you estimated to come up with a predicted value of distance in this case. So now let's move on to the third worksheet that we were active on during our lecture period. So this covers sections 3.3 to 3.5. Question 1, there was a plot and you were asked to describe the trends. First thing for you to notice, of course, is that there's 2 different variables here, grazed and ungrazed, and it's pretty clear that they should actually probably be fitted with 2 separate lines. Okay. When we look at them, you can see that they're both positive and both linear. For each of the treatments, there's relatively little scatter around the fitted lines, so they fit those lines pretty well. They've got similar slopes, but obviously they're going to cut through the y-axis at different points. So they're going to have different y-intercepts. So in terms of a regression equation, the B1, the slope would be quite similar, but the B0 is going to be different. In question 2, you were first given a couple of R values and asked to interpret them. The first one, 0.93, is obviously getting really close to +1, which is the maximum value you can have for a correlation coefficient. So I'd describe this by saying it's going to be a very strong association, it's a positive association, and it's also a linear association. The second one, R equals 0, in this case, what it means is we've got a flat line. So an increase in X has no impact on the value of Y. So essentially we've got no relationship at all. You will then have 2 graphs to look at and come up with an approximate R value. The one on the left obviously had a really strange value up in the top right corner. If we were to draw a line that tried to be the line of best fit, it would obviously go from the bottom left corner to the top right corner, okay, kind of diagonally up. However, this obviously doesn't represent a majority of the data points and is really just heavily influenced by just one, the value up there, the outlier, we would call it. So in this case, we would likely potentially eliminate it. If we did that and just did a line of best fit for the remaining values, we'd get a flat line down the bottom. So in that case, our R value would be somewhere around 0. For the figure on the right, clearly this is not a straight line relationship. It's a curve relationship, so it is inappropriate for us to actually fit a correlation, to calculate a correlation coefficient in this case. In question 3, there was a data set with the years from 1850 to 1930 and the associated Australian population size. When we look at the graph of this data, we can see that obviously it's a very good fit. It's linear, it's positive. The points do not fall very far from the line, so it's a close fit. So what we could also say is that the residuals are small. If we had to estimate what the correlation coefficient, the R, might be, it's going to be pretty close to +1. You're then asked to predict a value, the population size for 2016. So you can see the equation is given there right on the graph, okay? So the beta 0, the y-intercept is -136.3, and the slope, beta 1, is 0.074. So we can use that equation to plug in the X value that we've been given, which is 2016, and we come up with an overall population of 12.884 million people. Now, obviously, there were a lot more people. The population size of Australia was a lot bigger than just under 13 million in 2016. So in this case, in this instance, our regression equation has given us a gross underestimate for the population size. So if we look at a second graph here, we can get a bit of a clue into why this underestimate has occurred. And so when you look at this, you see the straight line of the regression equation that we use for the prediction. But when we actually see additional data values for after the data set, after our initial data set, so after 1930, you can see the relationship between the two variables changes. It's no longer a linear line. It begins to increase exponentially, okay? So the key message here, the big takeaway, is that we can't use a regression equation for prediction for data values, X values, which are outside the range of the values that were used to fit the regular regression equation, okay? Because as is clearly the instance here, we don't know if the trend will continue outside of the data set that we actually have. So that is the dangers of extrapolation and something that we avoid at all costs when we're undertaking regression. So the good news is that we're at the end of this brief video going through some of the answers and a bit of discussion about our worksheet activities for week 2. The second very good piece of good news is it's my birthday today. So I'm going to wrap up this video and go and have some cake. See you in class next week. Bye.